let's imagine that the water gives that ice that 1.50 times 10 to the fourth joules. How much more energy can the water give to the ice? Well, the water can still give an amount of energy, we'll call it Q3, which is Q1 minus Q2. In other words, 3.35 times 10 to the fourth joules minus 1.50 times 10 to the fourth joules, which equals 1.85 times 10 to the fourth joules. So the ice is now at 0 degrees. The water is still 1.85 times 10 to the fourth joules above 0 degrees, so to speak. So the water is going to continue to give energy to the ice. Well, how much energy would the ice absorb if all of it were to melt? Well, let's calculate that. To melt all of the ice, we'll call that Q4. That's a phase change. So we use the mass of the ice. We use the latent heat of fusion. Multiply the mass of the ice, 0.5 times 3.35 times 10 to the fifth. We get 1.68 times 10 to the fifth joules. Now, we notice that that energy is larger than the amount of energy the water can give. Notice, this is 10 to the fifth, that's 10 to the fourth. So the water does not have enough energy to melt all of the ice. The water would get down to 0 degrees before all of the ice had melted. Therefore, not all of the ice melts. How much ice melts? Well, how much energy is the water actually giving to the ice? The water can only give an amount of energy of 1.85 times 10 to the fourth joules, at which point the water will be at 0 degrees centigrade. The ice is already at 0 degrees centigrade as it's melting, so it's still at 0. Then we will have reached equilibrium and no more energy will transfer. So what we need to figure out is how much ice will that much energy melt? Well, how do we do that? Well, we know Q equals ml. If that's Q, we figure out what m is. So the amount of ice that will melt will be m, will be Q3 over the latent heat. In other words, 1.85 times 10 to the fourth joules divided by 3.35 times 10 to the fifth joules per kilogram, which is 0.0552 kilograms. In other words, 55.2 grams. So that is the mass of ice that melts. To answer the question, how much ice is left? Well, if we started out with 500 grams and we melted 55.2, we subtract that from the 500, leaving us 445 grams of ice. How much water do we have? Well, we melted 55.2 grams of ice, turning that into 55.2 grams of water, leaving us with 800 plus 55.2 grams, leaving us with a total of 855 grams of water. Notice, the total amount of ice and water initially has to equal the total amount of ice and water finally. In other words, 800 grams plus 500 grams is 1,300 grams. 445 grams plus 855 grams is 1,300 grams. The total amount has to be the same. Now, what is the final equilibrium temperature? Well, after the water has given up that 1.85 times 10 to the fourth joules, it has now cooled down to 0 degrees. The ice was in the process of melting, which it had to do at 0 degrees, so the final equilibrium temperature for this problem is 0 degrees centigrade. And that answers everything for this question. Now, it certainly didn't have to end up at 0 degrees, but just because of the amount of ice and water and their temperatures that we started with, this problem ended up at 0 degrees. Now, some of the homework problems will end up at other temperatures, either above 0 or below 0. So make sure to do those and practice those, for those of you in my class. What I'd like to do is actually try to solve this problem using a different approach, a completely different idea. We'll get a very similar answer. The answers will only be different because of rounding errors, but it's another way of thinking about the problem. Let's try that. We'll start out with exactly the same problem, but a different approach. Now, the idea is we've got water at 10 degrees and ice at negative 15 degrees. What we're going to do is imagine that we take one of these substances all the way to the temperature of the other substance. Now, the approach I'll use is, let's imagine we were to take this water at 10 degrees and remove as much energy from it as we would need to get it all the way down to negative 15 degrees. We'd have to cool the water, freeze the water, and then cool that frozen water, the ice, down to negative 15 degrees. We'll figure out how much energy that would take. But we can't remove any energy from the system. We then have to put it back in. So we'll put that back in and figure out what would happen to the ice after we put that back in. Now, why is that easier? Well, for some problems, it's a lot easier. But the idea is that if we were to get this water down to negative 15 degrees, we would have everything, 1,300 grams of ice. At negative 15 degrees, we would only have one type of substance to worry about at that point, and we're putting energy back into it. This actually is a much easier approach if you end up with a situation where everything is water or everything is ice. For this particular problem, it might not be that much easier, but for those problems where all of the ice melts, it really is much easier to take all of that ice and bring it up to the temperature of the water to begin with. If all of the water is going to freeze, it's really much easier to bring all of the water down to the initial temperature of the ice to begin with. So I'll actually do the approach where we take the water to the temperature of the ice first and see how that works, and then we'll go the other way around. We'll take the ice all the way up to the water and see how that works. And we'll get very, very similar answers. Okay, let's give it a try. So to cool the water down to the temperature of the ice, we'll have to do this in 3 steps. We first have to cool the water to 0 degrees centigrade. That is a temperature change. So we'll call that Q1 equals mc delta T. We use the mass of the water, 0.8 kilograms. The specific heat of water, 4186 joules per kilogram, degrees Celsius. We're cooling it from 10 degrees to 0. That's a temperature change. We'll just call it positive 10 of 10 degrees to give us 3.35 times 10 to the 4th joules. That's actually a number we calculated using the first method. Then, to freeze the water at 0 degrees, that 800 grams, that's a phase change. So Q2 is ml, 0.800 kilograms. Phase latent heat of fusion, 3.35 times 10 to the 5th joules per kilogram, giving us a total energy of 2.68 times 10 to the 5th joules. Then, to cool that frozen water down to negative 15 degrees, Q3 is again a temperature change, mc delta T. We use the original mass of the water, but now the heat capacity of ice and 15 degrees to give us 2.40 times 10 to the 4th joules. Adding them all up, we'll call that Q4, which is 3.26 times 10 to the 5th joules. So, let's imagine we remove that Q4, 3.26 times 10 to the 5th joules, from the water. We now have turned it into 800 grams of ice at negative 15 degrees to give us a total of 1,300 grams or 1.300 kilograms of ice at negative 15 degrees centigrade. So to do that, we had to remove this energy. But we cannot really remove any energy from the system, so we're going to have to put it back in. So we now have 1,300 grams, 1.3 kilograms of ice at negative 15 degrees, and now let's add this energy back in. Well, what's the first thing we have to do to the ice? As we're adding energy, we have to warm it up to 0. So let's see how much energy we have to add in to warm it up to 0, and then how much to melt it, and etc., etc. So putting that energy back into the ice to warm the ice to 0 degrees, that will require an energy, we'll call it Q5 of mc delta T, where now the total mass of the ice is 1.3 kilograms. We use the specific heat of ice, 2,000, 2 times 10 to the 3. The temperature change from negative 15 to 0 is 15 degrees, giving us a total of 3.90 times 10 to the 4th joules. So, out of that 3.26 times 10 to the 5th, 3.9 times 10 to the fourth is required to warm up the ice to 0, which means we still have to add an amount of heat that's Q6, which we'll call Q6, which is Q4 minus Q5, or the 3.26 times 10 to the fifth minus the 3.90 times 10 to the fourth, leaving us with 2.87 times 10 to the fifth joules. We still have to add 2.87 times 10 to the fifth joules into the ice, which is now at 0 degrees. That's going to start to melt the ice. How much energy do we have to add to melt all of the ice? Well, to melt all of the ice, that's a phase change. Using the entire mass of the ice, latent heat of fusion for the ice, we get 4.36 times 10 to the fifth. Notice, 4.36 times 10 to the fifth is larger than 2.87 times 10 to the fifth. In other words, not all of the ice melts. Well, how much melts? How much energy do we still have to add to the ice? Remember, that is this amount. That's the amount of energy we still have to add to the ice. That will be the energy that will melt the ice. Let's figure out how much mass of ice that energy will melt. We're almost done. The mass of ice that will melt is then given by Q6 divided by the latent heat, or 2.87 times 10 to the fifth, divided by 3.35 times 10 to the fifth, or 0.857 kilograms, which is 857 grams. What is that? That is the mass of the ice that melts, which means that's the mass of water that we end up with, 857 grams of water. If we started out with 1,300 grams of ice and we lose 857 grams of it because it melts, we end up with 443 grams of ice, and that's how much ice we end up with, 443 grams. This is all happening as the ice is melting. That's when we have finally added all of the energy back into the ice, and it's melting, and we know it melts at 0 degrees, so our final equilibrium temperature is 0 degrees centigrade. Now you'll notice this is actually very, very close to what we got from the first method. It's only a couple grams off. It's only off on that last significant figure. And this comes about just because of rounding errors. So, very, very good. This is another approach that gets us to the same result. In this case, this approach is not necessarily easier than the first approach. They're both pretty complicated, but it's very important that you understand both of these approaches. Now, I actually want to do this one more time, but I'm going to use kind of the same second method. I'll refer to that the first way we did it as the first method, where it's kind of like how much to this one down, how much this up, this one down, this one up, this one down. In this case, I'll refer to this approach as the second method, but there are two ways of doing the second method. You can take the water all the way down to the ice and then warm up the ice, or you can take the ice all the way up to the water and cool down the water. For this one, we brought the water all the way down to the ice and then warmed up the ice. I want to do this one more time, bringing the ice all the way up to the temperature of the water and then cooling the water back down. And we should get a very similar answer. But I just want to do this one more time so you see how this goes through one more time, because I really want you to understand all of these different approaches. To bring the ice up to the temperature of the water, we're again going to have to do this in 3 steps. So, to warm the ice to 0 degrees, that's a temperature change, we'll call this Q1, 0.5 kilograms times, remember, specific heat of the ice, 2,000 times 15, or 1.5 times 10 to the fourth joules. To melt the ice at 0 degrees, phase change, 0.5 times 3.5 times 10 to the fifth, 1.68 times 10 to the fifth joules. And then to warm that melted ice up to 10 degrees, the temperature change, 0.5 times 4186 times 10, 2.09 times 10 to the fourth joules, for a total of Q4, 2.04 times 10 to the fifth joules. Now, let's imagine that we add that 2.04 times 10 to the fifth joules to the ice. What do we now have? Well, we've warmed that up to water at 10 degrees. We now have 1.3 kilograms of water at 10 degrees centigrade. Now, we have to remove that Q4. What's the first thing that's going to happen? Well, the water will start to cool down. How much energy will it take to cool it down to 0? And then how much energy will it take to freeze all of it, etc., etc. There we go. To cool the water to 0 degrees centigrade will require an energy, we'll call it Q5, mc delta T, 1.3 kilograms times 4186 times 10 degrees, or 5.44 times 10 to the 4th joules. Well, we can certainly remove that amount, so the amount of energy that we still need to remove, we'll call that Q6, will be Q4 minus this amount. We have to remove this amount. This amount will go into cooling the water to 0. So we have to remove an additional Q4 minus Q5, 2.04 times 10 to the 5th, minus 5.44 times 10 to the 4th, or 1.5 times 10 to the 5th joules. Now, the next thing that's going to happen is the water will start to freeze. To freeze all of the water would require Q7, which is ml, 1.3 times 3.35 times 10 to the 5th, or 4.36 times 10 to the 5th. Now we notice the 4.36 times 10 to the 5th is larger than the 1.5 times 10 to the 5th. We cannot remove enough energy to freeze all of the water. So, how much water will actually freeze? Well, the amount of energy that will be frozen by the removal of the 1.5 times 10 to the 5th joules. So what's that mass? How much water will freeze? Well, that'll be Q6, what we called Q6 over L, 1.5 times 10 to the 5th divided by 3.35 times 10 to the 5th, or 0.448 kilograms, or 448 grams. That will be the amount of water that freezes. So how much water do we have left? Well, that'll be 1,300 grams minus 448. We'll have 852 grams left. So we freeze 448 grams, so we end up with 448 grams of ice. We have 852 grams of water left, and the water was freezing, and so we end up at 0 degrees centigrade. Again, very, very similar results, only off by rounding errors from the other two solutions. Very, very good. Okay, so I think we have done this problem enough. I hope you think so too. There are some homework problems that kind of go through a whole series of things. Warming up water, cooling down water, warming up ice, cooling ice, freezing water, melting ice, that hopefully will get you all the way to be able to solve problems like this. Okay, well, I hope you enjoyed that. I'll see you next time.